Hey folks, how's it going? Glazer here. Hi, happy Friday. Congratulations on making it through your first week at Berkeley High. That's a serious accomplishment, especially after everything that happened last year, right? So video looks a little different today. I'm wanted to record in Loom because I want to talk about the lab that you guys worked on Thursday and show you some of the data and kind of talk through some of the data there. So wanted to be able to share my screen here for you. For your lab with 1.2 speed where the car was going down the ramp, okay, I saw a lot of good data tables there. And data tables should have looked something like this, okay? And there's one tricky thing here, and I don't love the way this is set up, but it is, okay? And you have to realize that we have trial 1 through 5 going down here, right? Trial 1, car rolls 10 centimeters. Trial 2, car rolls 20. 3 rolls 30. 4 rolls 40. That makes sense. And then you get to trial 5, and we shorten the distance, okay? So it's not, it doesn't sequentially go up. So just make sure you caught that for your data. And most of you did, okay? And then this column right here is the time during the beam interruption, right? So what you need to know for this is that these the photo gates, right, that are being used to measure the time, it's like an infrared light, okay? So if the infrared light is shining and then the car rolls through and breaks the infrared light, that's what's being timed. How long is that light being broken as the car rolls through? So that's the time during beam interruption that's measured in seconds, okay? And then the width of the domino right here, you notice, does not change. The domino is 1 inch wide, 2.54 centimeters. Okay, so this width does not change. And this is the tough conceptual part with this lab, because we talked about distance equals rate times time, right? So then rate or speed equals distance divided by time. That's how you're getting the numbers in this last column here. Okay, the distance you are using is 2.54 centimeters every time, because that's the width of the domino. That's how much of the domino passes through the photo gate. So even though we have distance over here in column 2, that's not the distance you're using to calculate speed. This is essentially where the speed is measured as it goes down the ramp. Okay, so to get this column right here, you take the width of your domino, which is 2.54 every time, and you divide it by the time during beam interruption, okay? And you should notice as the car rolls farther down the track, the speed goes up, okay? We're gonna look at the graph, except for this trial 5, which remember we bumped this back to 5, and oh, the speed is the lowest, all right? So that's what you should see right there. I gotta move this up a little bit here, okay? So that looks pretty good. And then I wanted to show you the graph, okay? And I'm just gonna scroll through to find, so this one looks really good, okay? I do want you all to draw lines for these, right? And we draw what's called a best fit line. So you're not gonna like connect, you don't have to connect each individual dot perfectly. Sometimes you do, okay? I'm actually gonna use this one as an example. Even though it says, sorry, that curve is so bad, this curve is not actually that bad. I think this curve is really good, actually. So I wanted to use this for a couple things, okay? 1, you should have a point at 0, 0. Boop, right there. Put a dot there. Because when the car has gone 0 centimeters, has rolled 0 centimeters, it has a speed of 0 centimeters per second, okay? So this helps your graph. And then you're going to kind of connect the dots. Yes, I might have tried to make this line go through the dots a little bit closer, but I also wanted to show you this because I want to show you that you don't have to. This is not really wrong, okay? It doesn't go exactly through all the dots, but the shape that it has is actually very accurate. So what you should notice with this shape is that the initial part here, right, the speed increases very quickly. Okay, and the speed keeps increasing as the car rolls down the ramp, right? Except eventually, what you should see is that the graph starts to flatten out, okay? And what I want you to think about is a couple things, okay? In this environment, in a real life environment, if you're rolling a car down a track and you expand that track to an infinite distance, so that car can roll forever. It will always be rolling down a slope. What's going to happen eventually to that car? Eventually, it will reach a speed in which it doesn't increase anymore, right? Eventually, the forces, which we will talk about a lot this year, of friction and air resistance, will be pushing back on that car so much that it will reach what we can call a terminal velocity. It will not speed up any faster than that top speed. Okay. So the graphs that did this was really good because what you would see if you continued this to infinity, that your line would eventually actually flatten out and your car would reach a maximum speed, a terminal velocity. Okay. In an actual classroom. Now, if you were to eliminate air resistance and you were to eliminate friction, right, then the car would continue speeding up infinitely, but that's not what's happening here. Okay, so that was really good. I wanted to show you this these graphs and these slides to make sure you kind of get that idea. Okay, awesome. There is a couple questions on your quiz about this today. We're going to go through the materials on your quiz in a review, so you will be ready for it. But overall, you all did a really good job on that lab. We're going to come back to this a lot. We're going to come back to this when we look at free fall. We'll come back to this idea of what happens as an object's speed increases in various different environments. Okay. Awesome. Y'all have a wonderful weekend. Get some rest. Yeah, I'll see you virtually in the classroom next week. And then I'll see you the week after that in real life. So stoked on that. Okay. Hope you all had a wonderful first week at Berkeley High and take it easy. Be well.